Okay, periodic basics and periodic trends. All right, let's talk about Mendeleev. He's a Russian chemist. Dmitry Mendeleev was the first to create a system of classifying elements in 1869. So this system laid the foundation for the modern periodic table. If you can look at it right here, it doesn't look a lot like what we know today, because initially it was organized based on the increasing atomic mass. As we now know, it's based on a lot of other factors, trends, but also increasing atomic number. The thing about this, though, is that the symbols of the elements are the same. And this is what's great about the periodic table. It's the same regardless of the language. Okay, so you'll look down here on this one, and you'll notice a lot of familiar symbols. Initially, scientists were skeptical of Mendeleev's periodic table, and that's because there was a couple things wrong with it until he predicted the existence of properties that haven't been discovered yet, which were later, about 10 years later, they were discovered. So using his periodic table and the trends that we're going to talk about that he recognized and noticed, he actually discovered elements before they were actually discovered. So periodic law. This is the physical and chemical properties of the elements are periodic functions of their atomic number. Okay, what this means is as the number of protons increases, certain properties repeat in a pattern periodically. Okay, periodically means certain intervals. So if you look at this image here, you see a lot of things that change as we go across and down the periodic table. We're going to discuss a few of those things later in this lesson. So the ionization energy increases, the electron affinity increase as we go from left to right. The electron affinity and the ionization increase as we go bottom to top. And the atomic radius decrease going down and to the left. There are 92 naturally occurring elements. Elements are going to be organized in rows or periods. And the length of each period is determined by the number of electrons that can occupy the sublevel being filled in that period. Okay? All that means is we go left to right, element to element to element, we are adding electrons. All elements in the same period have the same number of principal energy levels. So a lot of this is review. Okay? I want you to know that elements are also arranged vertically in the periodic table by their chemical properties. Okay, what this means is that elements within the same group share the same chemical properties. So for example, the alkali metals, and all in group 1, are all highly reactive, and they react with water. They react to water, okay? So it's not about the periods, it's about the groups. And that's what the groups are what share chemical properties. Okay? And that's related to the valence electrons. As we know, the group tells you the number of valence electrons as well. And this is what tells us how likely these elements are to form ionic compounds. So valence electrons. These are electrons found in the outermost principal energy level. The number of valence electrons for each group element is equal to the group number. So in this image, you'll see lithium and beryllium. Lithium from group 1, beryllium from group 2. If you look at the Bohr model for lithium, it shows that there's one valence electron. If you look at the Bohr model for beryllium, it shows that there are 2 valence electrons. And so what I want you to do, if you haven't done so in your periodic table, label it 1, 2, and then you're skipping the transition metals 3, 4, 5, 6, 7, 8. That'll be an easy way for you to determine how many valence electrons each element has. Okay, let's talk about periodic trends. The 3 periodic trends we're going to cover is atomic radius, ionization energy, and electronegativity. Periodic trends are different properties and how they change at regular intervals as we move across and down the periodic table. Now, a lot of this is based on different forces within the nucleus that we're going to talk about, but the big question we need to ask is, how is an atom held together? So how is it held together in the first place? And I'm going to answer that with two forces: electrostatic attraction and electrostatic repulsion. Electrostatic attraction is it's the force between protons and electrons. Okay, so they are oppositely charged, so we know they're attracted to each other. Electrostatic repulsion, on the other hand, is the force between electrons within the atom. So repulsion also would talk about two protons, but we're not discussing that. We're not talking about the nucleus today. We're talking about different trends. Okay, so just ignore that. We're talking about electrons. We talk about electrostatic repulsion. Okay, so let's go ahead down here and look at our first trend that we're going to talk about. It is atomic radius. And so before we begin, let's just go ahead and let's define atomic radius. It is the distance between the nucleus and the valence electrons, so the outermost electrons. Okay, so first let's just take a look at two elements here. We're going to look at lithium and fluorine. Okay, lithium I'm going to put right here in this periodic table in red. Fluorine, might as well just choose green for it over here. So one on the far left and one on the far right. And let's go ahead and we know that lithium has 3 total electrons, and because it's in that first group there, it's going to have 1 valence electron. I'm going to draw a pretty wide shell here, and you should do the same, something like that. And I'm going to give lithium 1 valence electron. And then for fluorine, I'm going to draw a tighter little shell here, okay? Now fluorine, because it's in that 17th group, it's going to have 7 valence electrons. Let's go ahead and draw those in. 1, 2, 3, 4, 5, 6, 7. Okay, now going back to what governs these periodic trends, we're talking about two forces: electrostatic attraction, electrostatic repulsion. And these forces have a lot to do with the structure of the atom, and therefore they have a lot to do with the properties and behavior of the atom as well. So we're going to talk about a new concept here called electron shielding before we finish this diagram up here and explain. Electron shielding is a repulsive force, again, a repulsive force, but this one is specific to repulsive force of inner electrons and valence electrons, okay? So let's look at that. What does electron shielding look like? Well, you see lithium here, and I drew a bigger outer shell, didn't I? Well, let's look at why. Lithium is going to be shielded. The inner electrons are going to shield with that repulsive force that outer electron. There's two of them. There's two inner electrons here for lithium. There's only one valence electron. So those two are going to push up more consistently and repel that electron more consistently outward. Fluorine, on the other hand, it's got a 2 versus 7 situation going on here. These two inner electrons are going to repel those valence electrons, but they're not going to win that battle, okay? So eventually, that orbital, that outer valence orbital or energy level is going to get smaller and smaller. The result being a smaller atomic radius. And we can see that over here as we draw this in. Our first trend, the atomic radius decreases left to right across the periodic table, okay? As we go down, we're adding energy levels. So naturally, as we add energy levels, we are increasing our radius. Let's talk about cations versus anions as it pertains to atomic radius now. Cations, right here, let's look at the cation for lithium, so we have the neutral atom here, and we have a cation here. Well, a cation is positive charged. That means it has less electrons. So simply because it has fewer electrons, cations are always smaller than anions or neutral atoms. Okay? So simply not having that valence electron or that extra electron, it's going to make the shell smaller. Okay? Anions, on the other hand, if you look here, you see the fluorine anion. Fluorine is most likely to be a negatively charged atom. So it's going to have extra outer electrons there, outer valence electrons. So instead of being, like that concept we talked about earlier, electron shielding, instead of it being 2 to 7, all of a sudden it's 2 to 8. So these inner electrons are even more of a disadvantage trying to repel and push out those valence electrons. So therefore, anions are always smaller. All right, let's talk about our second periodic trend here. It's called ionization energy. Ionization energy is the energy required to remove a valence electron. Okay, so what this is saying is how much energy is required to turn an atom into an ion, a neutral atom into an ion. So what we're talking about is these bad boys right here. Okay, how much energy is required to remove them by something else, by another element. Okay, so we know that as we go from left to right down the periodic table, the number of protons increases. Okay, so over here we have less protons. Over here we have more protons. So therefore we have less attractive force. Over here we have more attractive force. And so what that's saying is the force between the protons here and the electron, the valence electron here, is less. It's not as strong because it's further in distance, because the atomic radius is larger here than it is over here. And it's greater to the right. It's greater in beryllium or boron than it is lithium, because there's actually just more protons pulling on those valence electrons. Okay? So the two things that are going to determine that are distance. So this is the distance between the protons and the electrons, and just the number of protons. Okay? So our next trend is going to be ionization energy increases, going from left to right. Okay? So let's go ahead and look at how it changes going from top to bottom here, down the group. Okay? So, because our atomic radius increases as we go down, so we'll go small AR, large AR. That means that we have a large attractive force, small attractive force. Okay? And this is kind of the same concept. We're talking about the two things that determine ionization energy are the distance. So the distance between the protons and the electrons, and the number of protons. So our number of protons increases, but the distance between the nucleus here and the electrons increases quite a bit. So as we go down, our ionization energy decreases. Okay, so they're less likely to be ionized. So while we're here, why don't we just go ahead and if you haven't done this on your periodic table, you should do so. But just know that these elements here are likely to be +1 ions. They are likely to lose an electron. They want to get rid of it so that they can be stable. And that trend continues this way. All right. And then our noble gases here, of course, at the very end. Not likely to become ions because they are non-reactive. They have a full outer shell. Okay, our last periodic trend is electronegativity. So we're going to call electronegativity the ability of an atom to attract electrons. Okay, we're also going to call this electron hogging. What it really says is how likely is this atom, how likely is it to steal an electron from another atom? So let's go ahead and look at lithium, beryllium, and boron going across the periodic table. And what we know is that lithium has fewer protons. So it has a less attractive force. Okay, so it's got fewer positive charges. It's got less of a force to pull in those negatively charged electrons. Okay, because of that, it also has a larger atomic radius we talked about earlier because of the electron shielding. Okay, over here we have boron now. Boron has more protons, so more electrostatic attraction. Okay, so if we just look over here, we will find, I want you to go ahead and do this. We've got fluorine, okay? Fluorine is the most electronegative element on the periodic table. It is the furthest to the right and the furthest upward, other than the noble gases, which we know are not reactive at all. So if we eliminate the noble gases, fluorine is the furthest up and to the right. So electronegativity increases going from left to right on the periodic table. Let's go ahead and see how it works going down. Okay, so lithium has lower atomic radius because it has less energy levels than potassium, which has a higher atomic radius. Therefore, it's got less distance between the nucleus and the atom's valence electrons. And this down here has more distance between the nucleus and the valence electrons. So because of that, the electronegativity decreases as we go down, right? Because lithium here is going to be more likely to steal that electron because it's a lot closer than potassium. We have a greater distance here, okay? So just to go over, just to review, there are factors at play here that dictate these periodic trends that we've talked about. Let's just go over them again. 1, the nuclear charge. So the number of protons in the nucleus is going to determine these trends: the atomic size of the atomic radius, electronegativity, and ionization energy. The second one is going to be electron shielding. So the ratio of those inner electrons to the outer electrons is going to determine your atomic radius, and therefore the other two as well. And distance is a big one. The distance between the positively charged nucleus and the valence electrons.